there's a region with uniform 0.5 Tesla magnetic field up to this point. There is no magnetic field beyond this point. A rectangular conducting coil with 20 turns and 3 ohm resistance riding on a frictionless cart is being pulled out of the magnetic field to the right at a constant 0.2 meters per second. The coil has a height of 0.4 meters and a width of 0.8 meters. Find A, the direction of the induced current in the coil, B, the induced EMF in the coil, and C, the pulling force. A. For the direction of the induced current, let's look at the magnetic flux. As the loop gets pulled out of the magnetic field, the magnetic flux decreases. That means the original magnetic field and the induced current's magnetic field, they must be in the same direction. The original magnetic field are those dots coming out of the page, so we want the induced current to give us a out of the page magnetic field as well. So if I use my 4 fingers to point out of the page, my thumb would have to go counterclockwise. That means the induced current must be counterclockwise. So the current in the coil must go to the right, up, to the left, and down. B. To find the induced EMF, we can start with the Faraday's law of induction, the negative n times the delta phi b over delta t. Now I'm just not going to worry about the sign. N is the number of loops, and the phi b is b times a in this case. So this is that. Since in this case the magnetic field does not change, b is a constant, so we can take the b out of the delta, leaving this part, delta A over delta T here. And this delta A over delta T is actually the same as what we covered in the last lesson. When the spark gets pulled with a speed v, the delta A over delta T is L times v, because that's the area change. So when this loop gets pulled, the loop in 1 second it may get to here. That means the decrease in area in 1 second will be from here to here, this area. And that area will be the distance traveled in 1 second, v, times the height of this. So the delta A over delta T is just the same as the L times v. So this is also N times BLV. In fact, we didn't have to start from the Faraday's law of induction. We can just use the BLV directly. So the number of loops is 20. The strength of the magnetic field 0.5. The L, do we use 0.8 or 0.4? We would use 0.4 because when this loop gets pulled to the right, the changing area is this part right here, which has the distance traveled in 1 second, that's v, times the height of the loop, that's 0.4. And then the v is 0.2. So this will give us 0.8. And what's the unit for induced EMF? It's volts. So this is the answer for part B. Another reason why the L we use here is the 0.4, not the 0.8, is because as the loop gets pulled out, this line does not cut through magnetic field lines. This line does not either. It's this over here. As this line moves, it cuts through the magnetic field lines. When it cuts through the magnetic field lines, that means a line used to be inside the coil, now it's outside the coil. That's what's causing the change in magnetic flux. So that's the length we use over here. Now let's look at the pulling force. The loop is being pulled to the right at a constant velocity, which means the acceleration is 0, so the net force is 0. The pulling force is just the force that's required to overcome that magnetic resistant force. And the reason why we have a magnetic resistant force is because we have this induced current that's inside the magnetic field. Now this segment of the current is outside the magnetic field. So it's just the magnetic force acting on 3 segments of the current. So let's see, if I use L cross B, I get the magnetic force on the top segment going upward. The magnetic force on the bottom segment goes L cross B down this way. The magnetic force on this current would go L cross B to the left. Now, of course, these two forces, they would cancel because they are equal. So this is the only magnetic force that's left we have to overcome. So this is the magnetic resistance force. The magnetic resistance force goes to the left, the pulling force to the right. And this force is caused by this current being inside the magnetic field. So this is ILB. And the current in the wire coil would be the voltage divided by the resistance. So it's the EMF divided by the resistance. And the EMF is 0.8. The resistance is 3 ohms. The L here is not the 0.8 but the 0.4. Because the magnetic force on these two, they cancel, they're equal and opposite. So the force we're considering is the force acting on this 0.4 meters of the current. So that's 0.4 and the B is 0.5, so we'll get 0.0533 newtons. And in this case, the coil gets pulled out of the magnetic field, the flux is decreasing. That's why the magnetic force pushes outward, trying to make this loop bigger to keep the flux from decreasing. And it is reasonable that the magnetic resistance force will go to the left because the loop is being pulled to the right.